Okay, so today what we're going to talk about are pair potentials. And these are different models for describing the potential energy between pairs of particles. We're going to talk about three different potentials. The Coulomb potential, which is a potential that describes the interaction between charged particles. So typically we're going to think about things like electrons and protons and describe their interaction through the Coulomb potential. That's not the only context in which you might think about charged particles. You might think about the interaction between ions. You might think about if you study semiconductor devices or photovoltaics, you'll talk about electron hole pairs or excitons, and the Coulomb potential comes into play with electron hole pairs as well. We'll talk about the harmonic potential as a model for the intramolecular potential between bonded atom pairs. So imagine like a diatomic molecule like I've drawn here. So you might have, for example, OH. This is the oxygen atom in red, and blue is the H atom. So simple diatomic molecule, and there is a potential energy as a function of the separation between the O and the H atom. Similarly, with the Coulomb potential, if I didn't say it, there's a separation between the positive and the negative charge. We're always going to call this separation R in this lecture today. And so there's a potential energy as a function of that separation. And then finally, we'll talk about the Lennard-Jones potential, which we use to model the intermolecular potential between two non-bonded polarizable atoms or molecules. And again, there's like a separation between those atoms, which we'll call R. And so you could think about, for example, the noble gases are really good examples of atoms which are polarizable that don't really participate in bonding, but you could have, for example, two helium atoms separated by some separation R, or the argon atom separated by some separation R, and so on. And they would experience a potential. A lot of times we call that a van der Waals interaction, right? It's not really a bonded pair experiencing a potential, and it's certainly not just a simple set of charged particles like the Coulomb potential, but it certainly experiences a potential. And we use something called the Lennard-Jones model to describe that potential. Okay, so one of the things that I want to discuss is the relationship between potential and force. And so this is a pretty fundamental concept, okay, in physics and physical chemistry. And it's going to be pretty important. So there is a relationship between force and the potential energy. And one thing that you can think about is that the potential energy actually gives rise to a force experienced by the object, which is experiencing the potential. So, okay, mathematically, we can actually make the statement quantitative. We can say that the force is equal to the negative derivative of the potential with respect to space, okay? And so we're using, in all of these three potentials, we're using R as the variable to represent the spatial separation of our coordinates. So what we really mean in this case is that we want a derivative with respect to the variable R of our potential, where the potential is a function of R. Okay, so first thing that I want to justify to you is that this makes sense from the point of view of dimensional analysis. Okay, so is this statement dimensionally correct? Well, let's find out, okay? So first thing that I want to do for you is I want to remind you of two statements that we made before, right? So we looked at the dimensionality of force, right? Where we said that we could take Newton's law, which is force is equal to mass times acceleration, and we could basically use that statement to figure out, well, what are the dimensions of force, okay? So the dimensions of mass are mass, which we denote with capital M. So that's m to the 1 for mass. And then acceleration, right, is equal to the change in position with respect to the change in time squared, right? So basically what it is, acceleration has dimensions of length to the 1 power times time to the minus 2 power, okay? All right, so this should be the dimensions of force. Mass to the 1, length to the 1, time to the negative 2, okay? Now, let's look at energy, and we used E equals mc squared to get at energy, right? Where again, we've got mass first. So in the first term, we have mass to the 1, and then c is the speed of light, and c squared is the speed of light squared. So the dimensionality of the speed of light squared is length squared over time squared. So overall, energy has dimensions mass to the 1, L to the 2, T to the minus 2, okay? And so then we look at this statement, right, that we wrote here, where we said that, okay, let's take the potential, which is an energy, right? The potential has dimensions of energy, and let's take a derivative with respect to R, okay? And so then really basically what we have to figure out is, well, what is the dimensionality of this derivative with respect to R, okay? And it turns out that dr, okay, so the numerator has does not carry with it any particular dimensions. The denominator has dimensions of length, okay? And so what the dimensionality of this derivative operator is length to the minus 1, right? And let me just take a minute to sort of justify that statement as well. You know, if we wanted to take the derivative of the potential with respect to R, and we didn't know how to do, the math to actually find the derivative, we could use this idea that the derivative tells us about the slope, okay? And so what we could do is we could say, okay, well, the derivative with respect to R of V of R basically is approximately equal to V of R, some particular value of R, which I'm going to call R2, minus V at some other value of R, which I'm going to call R1, divided by R2 minus R1, okay? And then this is basically, right, this is a way of getting the slope, right? This is the rise of the function and divided by the run of the function, okay? So rise over run. And remember what we're doing here in the numerator is we're subtracting an energy from an energy. So that doesn't change the dimensions of the numerator. And in the denominator, we're subtracting a position from a position, or a length from a length. So that doesn't change the dimensionality of the denominator. So overall, I've got energy divided by length, okay? And so the dimensionality of energy divided by length, of course, from what we just said up here, must be mass to the 1, length to the 2, t to the minus 2, divided by length, which is overall going to be mass to the 1, length to the 1, t to the minus 2. And that's what we determined is the dimensions of force, okay? So this statement is correct. Okay, dimensionally, this makes sense. That's what we've shown here, is that taking the derivative with respect to a length variable of the potential could plausibly yield a force because the dimensionality is correct. Okay, now the other question is this negative sign. It helps to actually see some of these potentials before we make our assessment if our negative sign is correct. But at least at this point, what we've done is we've made an argument that the derivative with respect to a length variable of our potential should yield a force, because that makes dimensional sense. Okay, so now we're going to move on to our first example of a pair potential, which is called the Coulomb potential, which describes the potential energy of two charged particles which are separated by some distance r. Okay, and these particles can have any charge. We're going to call, we're just, for the sake of convenience, we're going to call one of these particles particle 1. So we'll make the proton particle 1, and we'll make the electron particle 2. Doesn't matter, we could switch the order if we wanted, okay? So then Q1 is going to be the charge, the fundamental charge, which we'll call E, and Q2 is going to be equal to the negative of the fundamental charge, which we'll call negative E. And let's see, what is this value? So this is a very small amount of charge, right? Something like 1.602 times 10 to the minus 19 coulombs. Okay. So that's the charge of the electron and the proton, respectively, in SI units. Okay. And overall, by the way, this has dimensions of charge, right? Okay, so what's the actual Coulomb potential for the separation between these two things? So V of R is equal to Q1 times Q2 divided by 4 pi epsilon naught R, okay? So just a couple of side notes about this potential, right? The magnitude is proportional to the product of Q1 and Q2, and the magnitude is inversely proportional to, okay? So the larger the product of Q1 and Q2, the larger the magnitude of the potential, and the larger the separation between Q1 and Q2, the smaller the magnitude of the potential. Okay. The sign of Q1 and Q2 is also important. So when Q1 times Q2 is a positive number, then the potential overall is going to be positive. And when the product of Q1 and Q2 is a negative number, the potential overall is going to be negative. Okay. And so what's a negative potential mean? Well, a negative potential is attractive. So V of R less than 0. Potential is attractive. And that means it's energetically favorable to have particles close to one another. Okay. Let's take a peek at what this potential looks like. I'm going to draw a picture of it. Let me make a little bit of space. By the way, let me reverse this statement too. So let's change things. Phi is greater than 0. Then what do we have? Potential is repulsive. And it is not energetically favorable to have particles close to one another. Okay? So attractive potential, it's energetically favorable to have the particles close to each other. V of R is positive. It's a repulsive potential, not energetically favorable to have particles close to each other. All right, let's make a little bit of space for a plot. Okay. And let's just think about what this plot should look like. So along my y-axis, I'm going to actually plot the potential, and along my x-axis, I'm going to plot the separation, okay? So let's just have this separation called R, and then we'll plot the potential in red. I have a curve called V of R, okay? So, as we said, the potential between an electron and a proton is always negative because the product of Q1 and Q2 is always negative. So I just want to think about what happens first at large R. So as R goes to infinity, what happens is the potential goes to 0 and it approaches 0 from below, right? Because the potential is always negative, so it's approaching 0 from below. As R becomes small and approaches 0, right, then the potential looks like Q1, Q2 divided by 0, and anything divided by 0 is approaching either positive or negative infinity. In this case, it's negative infinity, so the potential is dropping to negative infinity. So this is basically what the potential looks like. Let me draw it again. This doesn't look so good. Try to make this blue line here very long. Okay. Okay, so there's this deep hole for the potential that these two charged particles can fall into. Okay. The separation, by the way, is always positive by definition. The definition of R, I'm just going to draw it again. I had drawn it in a previous edit of the slide and it got out of place. Okay, so if I can use any coordinate system I want the two charges, but let's just use Cartesian coordinates, x, y, and z coordinates for particle 1 and particle 2. So in that coordinate system, the way that I define r is I simply take the square root of the sum of the squared sums of the differences of the sum of the squares of the differences of those positions. So I have an x coordinate for particle 1 called x1 and an x coordinate for particle 2 called x2. Difference between those two coordinates squared plus difference between y coordinates squared plus difference between z coordinates squared. Sorry about that, I ran out of room. Hopefully you get the picture. Let me erase this and just draw one more time with more clarity. Okay. x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. This is what r is. R is equal to this. Okay, so r has to be positive. It can be 0 when x1 is equal to x2 and y1 is equal to y2 and z1 is equal to z2. That's the limit when the particles are overlapping each other. But it has to be positive. Or 0. Okay. Let's take this opportunity to also talk about the force, right? So let's remember that we said a couple things about the force. Force, F of r is equal to negative d dr of v of r, okay? So if I take the derivative of this Coulomb potential with respect to r, right, I can do, let me rewrite the potential ever so slightly. I'll write it as q1, q2, r to the minus 1 divided by 4 pi epsilon naught. It's exactly the same formula, just expressed in a slightly different way. And now, the way I've written it, right, I have my one variable, there's only one variable in this equation, which now I'm writing in blue, right? So if I take the derivative with respect to that one variable, all I'm going to do is I'm going to take this exponent, which is -1 in the variable, going to multiply the entire equation by that exponent, and then I am going to reduce the value of that exponent by 1, right? And decrement my exponent. So that means, let's just actually do that, is equal to -1 times q1, q2 over 4 pi epsilon naught times r to the minus 2, right? That's the derivative. Oops. That is the first derivative with respect to r of v of r, but remember I need to multiply this whole thing by -1, right? Because the force is not simply just the derivative, it's the derivative multiplied by -1. Okay? So, finally, that gives us an expression for f of r, which is equal to positive q1, positive q2, r to the minus 2 over 4 pi epsilon naught. Where did I get the positive 1, right? I had a -1 here and multiplied by a -1 here. So -1 times -1 gives me +1. Okay. So this is my Coulomb force, and probably more traditionally written like so. Q1, Q2 over 4 pi epsilon naught r squared. Okay? So that's the Coulomb force. And so let's draw this Coulomb force on top of our Coulomb potential. So it has the same limiting behaviors. It just goes there faster, right? So it goes to 0 more rapidly because r squared is in the denominator. So at large separations, it's going more quickly to 0. And it also goes to negative infinity more rapidly. So that means at some point it crosses over. It's, again, not very pretty, but that's what it is. Okay. I just want to say a couple of words about the direction that this force is pointing. Okay. So this force is always negative, just like the potential is always negative. So it's an attractive potential always, because it's always negative. And the force is also negative. So what does that mean, that the force is negative? Well, the force is a vector. So let's write that down. Okay, so the force is a vector, so it points in a direction. Which direction does this force point? Well, it's always negative, so Coulomb force between a negative and a positive charge always points in the negative r direction. So the force pulls minus charge closer to the positive charge. So that's what it means to be attractive, right? The force is pulling the charges together. Okay, so that's important. Okay, now let's look at the harmonic potential. So now I want to be a little bit careful to distinguish this potential from the Coulomb potential that we just talked about. So we're really talking about now two atoms which share a bond, okay? And again, as I mentioned before, this could be, oxygen atom, H atom, could be carbon atom, oxygen atom, could be H atom, F atom, could be, many, many different atoms. Could actually be more complicated molecules too that have, and you could think about all of the different bonded pairs in a polyatomic atom, and you could still think about the same harmonic potential. But now there's a difference, right? So the atom isn't just simply a single charged particle like the electron and the proton are. The hydrogen has 1 proton and 1 electron. That's the entire atom. The oxygen atom has 8 protons and 8 electrons. And so now we have those two atoms interacting through a very complicated set of, fundamental interactions that give rise to the chemical bond. and sort of this average interaction after, that accounts for all of those different microscopic, Coulombic interactions between all the charges, etc. We model with a potential called the harmonic potential. Okay. So the harmonic potential is really sweeping an awful lot of detail under the rug. But nevertheless, the idea is kind of the same. There's a separation between the oxygen and the hydrogen atoms, and we call that separation R. Okay. So again, we can write down a form for this potential, right? A mathematical expression, which I'm going to call V of R, is equal to 1/2 K R squared. Okay, and actually, just like before, let's be a little bit careful to color code what is a variable and what is not. Okay, so in this case, the variable is R, right? The separation. And K, it's not a variable, K is a constant. It's called the force constant. Okay. Why is it called the force constant? Okay, well, let's take our same idea as before. Let's use our expression that the force as a function of separation is equal to the negative derivative with respect to R of V of R, right? Okay, and now, right, so how do we do this operation? Negative d dr of 1/2 K R squared. Okay. So I need to again pull down this exponent, multiply everything by this exponent, and reduce the value of this exponent by 1 to take my derivative. And that is going to give me and multiply the whole thing by -1. It's going to give me minus K times R. That's my force. Okay. So F of R for the harmonic potential is minus KR. And there's a name for this. This is a particular expression called Hooke's law. Okay, and basically Hooke's law applies to a lot of different ideal systems, sometimes called ideal springs. The idea is basically the force not just the force, because again, the force has a sign, but the magnitude of the force is linearly proportional to displacement. Okay, that's a kind of in-word statement of Hooke's law. So let's draw these two potentials. Just like we did before. Let me give myself some room again. let's draw the potential and the force. That's what I meant. Okay, so myself a little coordinate axis here. In this case, R has a slightly different interpretation. Okay. R is really the separation between H and O relative to the equilibrium separation. And the equilibrium separation is typically some relatively small positive value. But what we've basically done is we sort of shifted, we kind of shifted our coordinate system to the left by the equilibrium separation. So in the way I've written this expression, the minimum of the potential occurs at R equals 0, right? And at R equals 0, we don't actually mean when H and O are right on top of each other. We mean that when when we are at the equilibrium separation, so then the difference between the actual separation and the equilibrium separation is 0. It's a little bit confusing. If that point is confusing to you, we can talk about it in class, and I can also make a modification to this expression so that it's not centered at 0, so that it is actually centered at the equilibrium position. That's not a problem. Okay. All right. But if it's centered at 0, the math is just a little bit cleaner. All right. So this is V of R. Okay. So you can see it's a parabola. Okay. And what this tells you is if I pull my atoms farther apart relative to the equilibrium, the potential energy goes up. And if I push my atoms closer together relative to the separation, the potential goes up, right? So having R greater than 0 means pulling them further away than the equilibrium, and having R less than 0 means pushing them closer together than the equilibrium. Okay. Now, let's also plot the Hooke's law of force. Okay. So the Hooke's law of force, let me do in red. And it's just the derivative of this parabola multiplied by -1. So it goes to 0 also at R equals 0. For R smaller than 0, right? When R is negative, I'm multiplying by -k, and k is some positive number. So when R is less than 0, I've got a positive force. When R is greater than 0, I've got a negative force. Okay, so basically, the Hooke's law of force looks like this red line. Right? What's the slope of this red line? Slope is k. And again, can we make an argument that the derivative multiplied by -1 of the potential gives me a proper force? So what happens when I push the atoms closer together than the equilibrium? The force is positive. So the force being positive means which direction is it pushing? It's pushing in the positive R direction, which means it's pushing in the direction of lengthening R, right? Getting back to the equilibrium. If I make the bond shorter than the equilibrium, the force pushes in the opposite direction, right? Back to equilibrium. If I stretch Beyond equilibrium, the force becomes negative, which means that the force is pointing to the minus r, restoring you back to the equilibrium. So the negative of the derivative of the potential seems to make sense for the direction of the force. Okay. The other thing that I'll say is that at the point where the potential is minimum, that's when the force is exactly equal to 0. So that idea is very important, right? Force goes to 0 at the equilibrium separation, which is where potential is a minimum. This isn't really something that we could realize with the Coulomb potential, right? The Coulomb potential continued to decrease towards negative infinity. It never turned around, right? So there wasn't really a minimum in the Coulomb potential, right? It continued to decrease towards negative infinity without bound. So the harmonic potential is a bit different, right? It actually has a minimum. It has a place where the force vanishes at the equilibrium. Okay, and our final potential that we'll see, the Lennard-Jones potential, also has an equilibrium position and a position where the force will vanish. Okay, and so the final potential we're going to talk about today is the Lennard-Jones potential. And this is now an intermolecular potential instead of an intramolecular potential. So we're no longer talking about two atoms that are bonded together. We could think about, for example, two noble gas particles. And then we're thinking about the separation between those two atom centers of those noble gas particles. We'll call that separation R. So once again, we're back to the idea of an absolute separation. So the smallest value of R is actually going to be 0. And that is not going to correspond to the equilibrium separation. That will correspond to these atoms being on top of each other. Okay, so first, again, let's just say that now there's a lot of complicated interactions that occur between these two argon atoms, for example, even if they're relatively simple, right? Oftentimes, when we talk about these things, we talk about, van der Waals, interactions. And that's the idea that, I tried to give kind of a hazy coloring to these atoms to denote that they have these electron clouds, which are squishy and can be deformed. So when you bring these argon atoms close to each other, right, they can deform each other's charge clouds and create, for example, these temporary dipoles, which can interact, right? So I just drew like a little instantaneous dipole where, for example, maybe the electron density on this argon atom on the left kind of rushes to the left side, creating a little intrinsic positive region on the right side, and then that induces dipole on the other argon, and so that's kind of the idea behind these van der Waals interactions, is that these two atoms polarize each other and have these induced dipole interactions. Okay, so it's a very complicated interaction. It's not just the interaction between two charged particles, and so then the question becomes, okay, well, how do you model this potential? And so the Lennard-Jones potential is an example of a model. And it's not the only model, but it is a model which is used for these van der Waals type interactions, relatively successfully. And it's also, in the grand scheme of things, a relatively simple model as well. So again, we have V of R. R is our separation variable. And it's the only variable in this potential. But there are other symbols that are going to come in, and I will explain those in due time. So, So, I basically have these two terms within this bracket, sigma divided by r, that whole quotient raised to the 12th power, minus sigma over r, that whole quotient raised to the 6th power. Okay, so basically we have two pieces here. We have a repulsive part and an attractive part. And the idea is that at certain separations, right, between these two argon atoms, I could have attractive interactions because of these induced dipole type van der Waals interactions. But if I make the separation too small, then basically I'm going to have overlapping charge clouds, which is going to have a lot of electron repulsion, and that's going to be repulsive. Okay. So the first term accounts for the repulsive part, the second term accounts for the attractive part, and they dominate in different regions of at different values of R. So at very small values of R, the repulsive part takes over. At very large values of R, the attractive part takes over. Or at larger values of R, the attractive part takes over. As at very large values of R, of course, because R is in the denominator of both of these terms, once again, we're going to see that the potential approaches zero from below. So let me go ahead to plot this potential. Again, this is R, and this is V of R. So V of R will actually approach positive infinity for very small separations and approach zero from below from large for large separations. Did I say? Yeah, approaches positive infinity for small separations. So as R goes to zero, right, I go to positive infinity. As R goes to positive infinity, I go to zero from below. There is a minimum or an equilibrium separation, which I'm going to call REQ right here. And that's where the potential is a minimum. And just a question for you all to think about. And we're going to discuss this in lab today. At this value, REQ, what would happen to the force? So remember, once again, the force for the Lennard-Jones system is going to be the negative derivative with respect to position of the potential. So if I take this derivative with respect to position, multiplied by -1, and evaluate it at REQ, what do I get? Right? What's going to be the result? What's going to be the actual value? That's a question. That's a question for you to think about. Okay. think about that question. We'll talk about it in lab. But let me say a few other things before we close for today. Okay. The other things that I want to say, I don't think I emphasized the dimensions of the harmonic potential like I did, or for the Coulomb potential. I probably should have emphasized both. Overall, this on the left-hand side, right, it's a potential, which is an energy, right? It has dimensions of energy, which I'll remind you again, mass, length squared, t to the minus 2. Okay, so that's on the left-hand side, which means on the right-hand side, everything has to be dimensions of energy as well, or dimensions of mass, length squared times time squared. So there are, in addition to the R variable, and the R variable certainly has dimensions of length, right? It's separation. We have a couple of things to consider, right? I have these other parameters. They're not variables, they're parameters. So they are fixed for a specific embodiment of the Lennard-Jones potential. When I say embodiment, I mean when I apply the Lennard-Jones potential to two argon atoms, that's one embodiment, right? I'm gonna apply this general potential to a specific system. So it's got parameters sigma and epsilon. Okay. So what should be the dimensions of epsilon, and what should be the dimensions of sigma? So overall, everything on the right-hand side has to have the same dimensions as energy, right? So mass, length squared over time squared. So it turns out that in order for that to be true, epsilon has to have these dimensions, mass times length squared times time to the minus 2. In other words, epsilon is an energy parameter. And sigma has to be a length parameter. And the reason why that has to be so is because in these brackets, I've got sigma over r raised to the 12th power minus sigma over r raised to the 6th power. Okay, so I'm taking a difference between two terms, and those terms are raised to different powers. So the only way for that to be valid dimensionally is for those terms individually to have no dimensions, right? If for example, if we had each term individually having dimensions of L, right, within the parentheses, then I would have L to the 12 minus L to the 6. And that wouldn't make any sense, right? I cannot subtract a dimensional quantity, which is L to the 12, and L to the 6, right? Because subtraction cannot change dimension. So the only option is for these terms, sigma over r, to have no dimensions, which means that whatever the dimensions of r are, I have to have the same dimensions of sigma, so that division of those two terms leads to no dimensions. So sigma has to have the same dimensions as r, and r is a length dimension. So sigma is a length dimension. So then I end up having length divided by length raised to the 12th power minus length divided by length raised to the 6th power. So I have dimensionless quantity minus dimensionless quantity. Everything within this has no dimensions, so the only thing which is left over to have any dimensions is epsilon, and epsilon must have the same dimensions then as V, which is an energy. So epsilon has to be an energetic term. It has to be a term that has dimensions of mass times length squared over time squared. Okay. So then once you appreciate the dimensionality of sigma and epsilon, then what you can actually realize is that they relate to features of the system that they model, and in particular, sigma is, because it's a length parameter, it's related to what we call the van der Waals radius of the system. Okay. So some notion of the size of these particles right, is encapsulated in this sigma value. So in fact, I think what it's fair to say is that sigma, I'll have to double check this, sigma is either half the rate, I think it's basically sigma over 2 is basically the center of the atom to the edge of what we envision as this polarizable charge cloud, sort of like the edge of the atom. So that I could, in fact, have two, if I had these atom clouds exactly touching, so let me try to redraw this. So imagine atom 1 here at the center, atom 2 here at the center, and the distance between these two being sigma. Then basically what these, how I could envision the charge clouds is like the edge of one charge cloud would be here. The edge of the other charge cloud would be here. Right, so some notion of the atomic radius. Is encapsulated in sigma. There's also the equilibrium separation between those two particles is also related to sigma. Has a very funny value. So this R equilibrium occurs, the equilibrium separation happens to be at the value 2 raised to the 1/6 times sigma. And so basically if you make the R in the denominator 2 to the 1/6 power sigma, then what ends up happening is you get something like -1 in this quotient here, and then this value right here is something like -4 epsilon, or perhaps it's just negative epsilon. I do apologize. We'll have to actually work this out in lab. There's something significant that happens when R is equal to 2 to the 1/6 power sigma, and you can figure it out just by plugging the value in, and then you get the value of the minimum of the potential at that value of the separation, and it's closely related to the magnitude of epsilon. I'm going to actually just wager a guess that what you get is negative epsilon. But we're going to verify in lab. Okay. So that's the other point, is that epsilon is related to the depth of the potential well. Okay. So the deeper the potential well, meaning the larger the magnitude of epsilon, right, the more attractive the interaction is at the equilibrium separation. Okay. You can actually take the derivative of this potential to get the force, right? The negative derivative of this potential to get the force. It's a little bit, nasty because you have these exponents. It's not that bad. We're going to also do it in lab numerically. And you'll get a force. The shape of the force ends up looking an awful lot like the potential. It's this kind of same kind of curve shape, right, as what you have for the potential. And again, you can make, some pretty interesting arguments. I think I've already asked you what should happen to the force at our equilibrium. But you can make some pretty interesting arguments, again, about the direction of the force depending on where you are, right? If you're to the left of our equilibrium, the direction of the force is positive, points in the direction of larger separation. If you're to the right of our equilibrium, the force is negative, points in the direction of negative separation, right? Pushes the things closer together. Okay, so we're going to explore this more in lab. I hope you found this helpful. Well, see you this afternoon.